if you take this Lie algebra invariant subspace and close it up, you get a group invariant subspace. And I just want to mention that that's not a trivial fact. If you look at SO2 acting by rotation on functions on the circle, the Lie algebra action is dd theta. So inside the smooth functions on the circle, you can look at functions that just live on the half circle. Perfectly good closed subspace of C infinity of the circle, and it's preserved by the Lie algebra because it's defined by a support condition, and differential operators don't change support, don't increase support. But this living only on a half circle, that condition is not preserved by the group, it's not preserved by rotation. And the reason that this example doesn't work out is that if you have a function in this space, if you make a bump function in this space, that its Taylor series doesn't converge to it. That's one of the basic facts in soft analysis, is you can make lots of bump functions, but they never have convergent Taylor series at the places where interesting things are happening. Okay, and well, so what's the formalism that Harishchandra got out of this example? So in these principal series for SL2R, if you impose the condition of finiteness under the rotation group, then you've got a Lie algebra representation which you could understand and study. In general, if you have real points of a connected complex reductive algebraic group, well, Jeff talked about this already. You can put the group inside matrices, and you can make it stable by transpose of matrices. So GLN, one of the most important facts about GLN is the polar decomposition, that any invertible matrix can be written uniquely as an orthogonal matrix times a positive definite symmetric matrix. And, well, a positive definite symmetric matrix has a unique logarithm, which is an arbitrary symmetric matrix. So this exhibits GLN topologically as a direct product of the orthogonal group and this vector space of symmetric matrices. So this polar decomposition is inherited by this algebraic subgroup. If you define K of R to be the intersection of the orthogonal group with, I should put G of R here, and S naught to be the symmetric matrices in the Lie algebra G, then this group G of R also has a topological product decomposition as this maximal compact subgroup times a vector space. Okay, so if I've got a nice representation, I'm sorry, I failed to change so many of the G's to G of R. Nice representation of G of R, then there are two things I can look at. One is I can look at the K of R finite vectors, the things that transform finitely under this compact subgroup. And I could also look at the smooth vectors, where this function from G of R to the vector space that just given by the action of G on an element is a differentiable function. And then I can define the Harishchandra module of the representation to be the intersection of these two subspaces, and it carries a representation of the Lie algebra, because everything's smooth, so I can differentiate the group action, and it carries a nice representation of this compact group K of R. And the last thing that I should have said is that these smooth K of R finite vectors this is dense in W. So that's the instruction. So now we can make an abelian category. So I'm gonna. It's useful to have this in more generality than G and K. So whenever you've got two real Lie algebras with containment and a compact group with Lie algebra little l that acts on the big Lie algebra by Lie algebra automorphisms, then you can define an H of R, L of R module. And that means a complex vector space that has representations of both the Lie algebra and the compact group. And the requirement is, first, that the compact group action should be locally finite, that every vector in the representation generates a finite dimensional space under the compact group. And the action on that finite dimensional space is continuous. I don't need a topology on W to make this definition, because this requirement of continuity is just on a finite dimensional subspace. And on a finite dimensional complex vector space, there's a distinguished topology. So there's no topology on W that's needed to make sense of this. Well, a continuous representation, finite dimensional representation of a Lie group is automatically smooth, analytic, so I can differentiate it and get a Lie algebra action. And the second condition is that this differentiated action is the restriction of the H of R action. And then there's some strange compatibility condition that I'm not going to worry about. And this next proposition is, that doesn't belong here. I'm going to explain that in a minute. But what belongs here is this statement, that if you have a representation of G of R on a complete locally convex W, then if you pass to smooth K finite vectors, you get a G of R, K of R module in this sense. And that's a functor. I mean, this category of topological representations, it's not an abelian category, but it's still a category, and this is a functor. And the big point here is that this this category of H of R, L of R modules has no topology. And it's therefore an abelian category. So in other words, you have kernels, co-kernels, short exact sequences, and all that nice abelian category stuff. So that's nice. Excuse me. So, well, as I say, this proposition got pasted in on the wrong slide somehow. What I want to do is take everything on this slide and complexify it. And I want to say a word about why complexifying is better. So the complex vector spaces are better than real vector spaces. And one reason that that's true is that on complex vector spaces, you can approximately diagonalize linear maps. But here's an example where you would think that you should use a real vector space, but you shouldn't. So if you want to study the motion of a pendulum, well, you know, this is a very primitive pendulum. It's given by a real valued function of time. The value of the function gives the angular displacement of the pendulum. And the differential equation that governs things in this mathematical world where everything is simpler is that differential equation. And the solutions of that differential equation are given by sines and cosines. But what I want to say is that it's easier not to study these real valued functions, but to study complex valued functions. Same differential equation, but allow complex valued functions. And then it's easier to solve the differential equation, and the solutions are given by complex exponentials, well, e to the I plus or minus lambda t, like that. It's easier to arrive at this than to arrive at that. And once you know these complex solutions, it's easy to identify the real valued ones inside. The condition to be real valued is that the second coefficient is the complex conjugate of the first one. So complex is better. But anyway, so how does this work on the level of Lie algebras? If you have a real Lie algebra, you can make a complex Lie algebra out of it by tensoring the real Lie algebra with C. So what that means is that this tensor product, formally it's the space of symbols x plus I, y, for x and y in the real Lie algebra. And you make this into a Lie algebra in the obvious way. You know, x bracket iy is I times x bracket y, and so on and so forth. We know that the structure theory for complex Lie algebras is a bit simpler to understand than the structure theory for real Lie algebras. And we're interested in doing representation theory. And the point is that if you have a representation of a real Lie algebra, that's exactly the same thing as a representation of the complexified Lie algebra. Here are the formulas. If you have this representation pi naught of the real Lie algebra, that defines a representation pi 1 of the complex Lie algebra by this formula. And of course, you get pi naught back from pi 1 just by restricting to the real points. So this identification is so perfect that I'll usually just write pi for both of those things. So if you're doing complex representation theory, you might as well complexify your Lie algebras. It's just easy. Same thing works for groups, and Jeff talked about this yesterday. If you have a compact group, or compact Lie group, you can put it inside some unitary group. And out of that subgroup of the unitary group, you can make a complex reductive algebraic group. What you do is you take this subgroup of the unitary group, and this Lie algebra L of R consists of skew Hermitian matrices. So I times L of R consists of Hermitian matrices, which is to say symmetric for the GLNC point of view. And so this formula turns out to define a complex reductive algebraic subgroup of GLNC. And this is the complexification of the compact group. So the way to say the same thing without, well, this embedding is sort of choosing coordinates. To define a complex algebraic group, you should say what the algebra of regular functions on this complex group is. And what it is, you take the complex valued functions on the compact group that transform finitely under left and right translation. That's a finitely generated complex algebra, and it just has all the structure to be the function algebra for a complex algebraic group. So when you set things up this way, any finite dimensional a finite dimensional continuous representation of this compact group is the same thing as a finite dimensional algebraic representation of the complexification, but it's same kind of formula as the x plus iy formula for Lie algebras. Again, this identification between pi naught and pi 1 is just perfect. So I'll just write the same letter for both of them. If you move into the world of infinite dimensional representations, the statement is that locally finite representations for this compact group are exactly the same thing as algebraic representations of the algebraic group. Okay, so we know how to complexify the notion of Lie algebra representation. We can complexify the notion of compact group representation. So now we can complexify these H of R, L of R modules. So if you complexify the setting from before, now we've got complex Lie algebras, and the small one is reductive. It's the Lie algebra of a reductive group, capital L, and this capital L acts algebraically on the Lie algebra H. And in that setting, you can define an HL module. This R here is one of the ones that should have been transferred to a G earlier. This should be a representation of L, not L of R. And that L action is supposed to be algebraic. The differential is this Lie algebra action, and then this compatibility. And I'll write M of H and L for this category of HL module. And now the statement is that passage to smooth K finite vectors gives you a functor from these group representations to GK modules. Okay, so again, it's worth noting that this definition of the category doesn't make any use of L being reductive. And it's useful to have that extension. okay, so so now we've got this category. So we've got this category M of GK, and it's abelian. And what we want to do is classify the irreducible modules, well, the irreducible objects in this category. And we want to do this but by imitating this BGG category O stuff, and that means that you want to use homological algebra. And one of the big ideas in category O, it's a big idea, so I'll put it in red, that there was this change of rings functor. U of G tensored over U of B with something. And we'd like to promote this to M of GK, and so I want change of rings functors. And in order to do that, I need rings. I need to realize I need to realize that this M of GK as modules over a ring. Okay, so that's what I want to do next. Yeah, so I want to make this category of GK modules into a category of modules over some ring. So part of what we're talking about, well, for H L of R modules, partly we're talking about representations of this Lie algebra H of R. And it's very well known how you make that into modules for a ring. You take the universal enveloping algebra. And then representations of this Lie algebra are the same thing as modules for the associative ring, the enveloping algebra. So I want to do the same thing for locally finite representations of the compact group. So the right algebra to use is this convolution algebra. So I want to look at measures, and this L's should be L of R's. I want to look at measures on the compact group L of R, which transform finitely under left and right translation. And well, distributions on a group, compactly supported distributions on a group are an algebra under convolution, and so these measures on L of R make a convolution algebra, and the Peter-Weil theorem says that algebra is isomorphic to the direct sum over irreducible representations of the group of the endomorphism algebra of the representation. So it's a direct sum of matrix algebras. Since they said, if I'd said complex valued measures, there'd be no R to worry about out here. And I don't want to talk about it carefully. But I wanted this slide to be all real. So use real value measures. So roughly, well, locally finite representations of this L of R are modules for this convolution algebra. So that's nice, but the tricky part is this convolution algebra doesn't have an identity element. So the identity element for convolution is a delta function at the identity. And the delta function at the identity doesn't transform finitely under group translation if the group is infinite. But that's okay. In this Peter-Weil isomorphism, if you have a finite set of irreducible representations, you can look at the measure corresponding to the sum of the identity operators on this finite set of representations. So you could write this down explicitly. It's the Haar measure on the group multiplied by more or less a sum of characters of these representations. These elements 1 sub alpha make what's called an approximate identity. If you have, in the convolution algebra, if you have any one of these L finite measures, then you can find some set of representations so that if you take any of these approximate identities that's big enough, that contains this alpha of R, then that approximate identity is an identity on R. So you can make the same definition for a module. You say that a module, well, remember that a module is called unitole if the identity element of the ring acts by the identity. So here our algebra doesn't have a unit, so we need the notion of approximately unitole. That means that for every element of the ring, well, big enough, good enough approximations to the identity act by 1. That's the statement. And now what's true is that a locally finite representation of this compact group L of R is exactly the same thing as an approximately unitole module for this Hecke algebra. So in other words, if I define, well, I write R mod for this category of approximately unitole modules, I've realized these locally finite representations as a module category for a ring. Okay.
Sorry, you realized the last one.
So the statement is, I want to do change of rings and things in these categories, and so I need a ring. And for the compact group representations, this ring of locally finite measures that transform finitely, the category of modules for that ring, approximately unitole modules for that ring, is exactly the same as the category of locally finite representations of the group. Okay, so now I can complexify all this stuff. And of course, the representations of the complex Lie algebra are just modules for the complex enveloping algebra. In the same way, given a reductive algebraic group L, if I write O of L for the algebra of regular functions, then I can define R of L to be the L finite linear functionals. So I look at I take the vector space of all regular functions, and I look at linear functionals on that vector space. the group L acts on those linear functionals, and I want to look at the linear functionals where it acts finitely. So that R of L is defined to be the L finite linear functionals. And it turns out, again, that looks like the direct sum over irreducible representations of these endomorphism algebras. The reason these linear functionals make an algebra, well, an algebra structure is some kind of map from the tensor product to R of L, and this map is just the transpose of the coproduct in the regular functions. So this algebraic group, there's a map of varieties from L cross L to L, given by group multiplication, and a map of varieties is the same thing as a map of regular functions in the other direction, and that's this coproduct on the algebra of regular functions on the group. And then you take the transpose of that, and that becomes the algebra structure on R of L. And again, there's approximate identities, and what's true is that algebraic representations of this algebraic group L are the same thing as approximately unital modules for this ring R of L. And, well, you can do the same thing. The fact that L was reductive doesn't matter here. Okay. Well, I want to put these things together. These HL categories have H and L interacting. And so here's the setting. I've got these big complex Lie algebra containing this L, the subalgebra, and a reductive algebraic group acting algebraically, Lie algebra automorphisms. And in this setting, then well, I don't want to belabor this too much, but you can make a kind of smash product of the enveloping algebra of H and this algebra of distributions, R of L, and there should probably be an L of R here. Well, this is vague, but this is a perfectly good associative algebra, and it has an approximate identity that it inherits from this subalgebra. And the statement is that this category of HL modules is the same thing as approximately unital modules